One of the more complicated accessories for the mill is the universal dividing head. It used to be very popular years ago when they were building a lot of gears, doing splines and stuff. The advent of the CNC in some cases has pretty well obsoleted the universal dividing head. But again, for the small machine shop who doesn't have CNC capabilities, a tremendous amount of very complicated work can be done with the universal dividing head. You'll notice we have the dividing head itself. It is capable of being able to tilt in this fashion depending upon the angle or pitch of work that we want to machine. We have the footstock on the other end, which again supports the work like the shaft that you see supported in there now. It is also adjustable for height, making it compatible with the head for different angles. The tailstock itself will also tilt and pivot with its center point in our workpiece. Now, a standard that has been established for all dividing heads is 40 revolutions of the hand crank per 1 revolution of the workpiece. So we have established a fixed base number to deal with in any type of divisions that we want to work with. Now, let's assume that on this shaft we wanted to machine 10 splines. We would simply divide 10 into 40, or 1/10 of 40, indicating 4 complete revolutions of the hand wheel in order to advance the part. Watch slowly as we show you an example of that. We'll simply go over to our hand wheel dial and establish a reference hole that we are working with. And this is called our dividing sector that you see here. Anytime that we get into a more complicated division of revolutions and fractions of revolutions, our sector comes into play. But for simple division, let's work with a 4 revolution or 10 splines in our part. We simply pull back on the spring-loaded handle in a clockwise fashion, 1 revolution, 2 revolutions, 3, and 4, and locate in the same hole. Okay, this has advanced our part 1/10 of a revolution. Very important to keep that in mind. You need to have your head on straight when you're dealing with a universal dividing head. There's some pretty good booklets available out there showing much more complicated divisions. Now, if we were to take again another division that had a fraction of a revolution, we're simply going to use our sector arms and count the number of holes between the sector arms on a given plate. And we'll show you a close-up on the plate. You're going to see a set of numbers stamped inside our plate. And these are number of holes in the circumference here that we're dealing with. Anytime that we break the circle up, we want to find a fraction that is divisible by one of these numbers. And that is the row of holes that we are going to use in order to break that up into a fraction of that revolution. On our particular sample here, we're set on row 39. We have 39 holes around the periphery of our index plate. So we would space our sector bars accordingly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hole spacings. If our math is correct, we would come around 1 revolution plus 11 holes in our sector and lock it into place. Now, in order to time that sector again, we simply rotate our sector bars to come in contact with our locating pin. Advance 1 more revolution, come up against our sector stop, and we're ready to repeat the process. Okay? So you can see that we can divide incrementally those divisions up in very, very fine graduations. We also have what we call a simple indexing of the dividing head as well, and that is located up at the top behind the headstock, if you will. We can see another large plate that has index holes, and we've got a rotating pin that we can lock in this fashion, and this engages it, eliminating any rotation at this point. And those are on 10-degree rotations. Let's count them here and see if it's 9 or 10 on that direct indexing plate. Okay, this has a direct index of 10 degrees around the periphery of that plate. So if we were working in any of those increments, we would simply use our rapid index points, lock in our pin, and we're ready to machine at that designated setting. Rotate our hand wheel in a clockwise fashion, lock our pin in place, and we're ready to go. When you're working on the dividing head, it's a good idea to keep a little notepad handy. Write that information down on the notepad or on a 3x5 card and keep it close at hand so we don't lose track of our sector settings or the number of rotations that we need in order to properly index the part. We don't want to be listening to Love Potion number 9 on the radio and lose track of the number of rotations or holes in our sector setting to achieve the proper division for our spline or gear that we may be cutting. Alright, now let's move on to what is called a super indexer. Again, a very versatile machine for a majority of indexing operations in the machine shop. Let me clear off the work table here. We'll install our super indexer and I'll be back with you in just a minute. This is our super indexer. One of my favorite tools in the shop. It's a great accessory for the mill. This particular model is a vertical and horizontal. In the horizontal mode, we can simply chuck something in the 3-jaw chuck. We can drill a hole pattern. It's very convenient, not quite as accurate as the rotary table, but for most general machine work, accurate enough to get you by. If we look at the bottom of the base, again, it has the same slots as our vise. So for rapid installation on the table, we would simply machine a block to fit into our keyway that goes into the keyway in the bed as well. So that'll give us rapid alignment. We don't have to spend a lot of time dialing in the part in order to get the shaft parallel to our x-axis. Alright, now let's spin it around. Let's take a look at the different degree settings on the side of the super indexer. We can see our reference mark and a 360 degree setting around the band of the 3-jaw chuck. Now if we're to turn over to the other side, this is what locks and releases our pin or hinge pin, allowing us to rotate the indexer. If we release that lever, it's spring-loaded. We pop into the next slot or tooth in the indexing sequence. If we turn our indexer around, we'll notice a plate on the back. In order to change plates, we simply remove the back and install the appropriate plate for the type of indexing that we want to do. This makes it very fast and easy. We don't have to worry about counting or watching the degree wheel. We simply release the lock lever, rotate it until it pops into the next setting, and we're automatically spaced. Right, if we pop our back, you'll notice that we have 24 teeth in our indexing gear. This is our release pin or lock pin here. We simply release it, rotate, the pin automatically locks in place. This is our permanent index plate that we have with 24 teeth that allows us to conveniently divide things every 15 degrees. 0, 15, 30, 45, 60, 75, and 90 degree increments. If we don't want to be bothered with 24 direct indexing points, each super indexer comes with a variety of secondary master plates, if you will, that will fit on the back of our super indexer, allowing us to rapid index in a variety of sequences. This one, for example, gives us indexing at 60 degree intervals. We've got another multi-interval here, again and again. This is a 4, so each time we index, we're going to be indexing at 90 degree intervals. Each Super Saver comes with a good selection of these plates, allowing you the ability to select the appropriate plate for the task at hand. We've got an index hole in the back and a little rivet or stud protruding from the plate. We'll simply align those two. You can see if we look around that we have blocked out all but 6 locations in our master 24 increment plate. So now as we advance the super indexer, we can only lock out in those appropriate locations. So this makes it very convenient when we want to mill a hex head, mill something with 8 sides, etc. Once we've installed our plate, I'm going to go back and install the backing plate which holds that in place. Put our 3 screws in, snug them up. We're now set to machine a hex head on the back of our wrench that we machined earlier with the profile cutter. This will allow us rapid indexing for a 6-sided nut. Let me take a few minutes to set it up, dial indicate our shaft in place, and I'll be with you in just a moment. Alright, we've mounted our indexer on the table. We're going to be using a 3/4 inch end mill. The diameter of our part is 1 inch ETD 150 round stock. We want to machine it so a 7/8 socket or wrench will fit over the end of it. So 7/8 from 1 inch is 125 thousandths divided by 2. So we're going to need to take 62.5 thousandths off of each flat in order to bring it into specification. We've locked our super indexer in. We've got a lock handle on the back side of our super indexer. Once we've made the necessary index, simply rotate the lock lever back, locking the spindle in place, giving us that extra added rigidity. Alright, let's go now. We'll bring our cutter over the top of our work, lock the spindle, elevate the bed until we just come in contact with our workpiece. We're going to set the dial on the Z-axis. We're going to raise the bed 62.5 thousandths. Lock our knee in place. Give our cutter a little shot of cutting fluid. A little bit on the part there. We're going to advance the cutter into the workpiece. All right, loosen our lock lever. Index to our next cam. Put our lock lever in place. We're ready to mill the next flat on our nut. You can see we've got our workpiece choked up pretty close to the chuck, again for added rigidity. So you can see with a few neat accessories for your mill, you're capable of machining some pretty snazzy parts. I'm kind of a tool nut at heart, so I've got a pretty good selection of tools for that emergency job. Sometimes the wife has a hard time understanding that. Just tell her it's a guy thing. All right, that was 5 of 6. We're on our last index. Okay, there we go. That was our 6th flat on the hex nut. Let's go ahead and wipe it off now and see if our socket fits. Voila! Excellent fit of the socket. Now, in order to complete the part, we're going to go ahead and take a file and we'll just break these sharp edges off around our hex nut. So there's a good example of what we can do quickly and efficiently with a super indexer. Very versatile, useful tool. Make sure you have it clamped down tight on the bed. Make sure that you've indicated it in correctly depending upon the machining application. You can also support a long workpiece with a tailstock like we showed with the universal dividing head. Keep that in your bag of tricks as well. Oftentimes we need to extend a large part out either for fluting, milling a flat, or a keyway on it, and we need to support that work. Let me grab that while we're talking about it so again you can get a better visualization of what we're dealing with. Okay, in this application you can see by having the footstock up at the end, it gives our work the extra rigidity that we need in order to either machine flats or a keyway along this shaft. Keep that in your bag of Indian tricks when you're dealing with a super indexer. We've shown you quite a selection of high-dollar accessories that are available for the mill, from a rotary table to a universal dividing head and a super indexer. Don't be intimidated though by the cost or size of these tools. Depending upon the job and the part that you are machining, you can build some simple tooling fixtures like we showed you earlier. Just a little bit of imagination and ingenuity is all that's required to get you into the production line. Let's take a few minutes and cover the tools necessary for proper inspection of our finished parts. Keep in mind the type of tools that are necessary directly depend upon the quality and preciseness of the work that you're doing. If you're working for automotive race car guys, if you're doing work for Farmer Brown down the road, we're not going to be dealing in 10,000ths of an inch in most cases. Usually plus or minus 2, 3, 4, 5,000ths is more than adequate for these industrial type applications. If you're building parts for aerospace or the military, by all means, they're going to require you have some pretty heavy-duty inspection equipment at your disposal. A pair of dial calipers, like I show in my hand, is going to cover, for all practical purposes, 99% of the work in general application, industrial applications, agricultural applications that you may encounter. It's also a good idea to have a good set of micrometers, a 0 to 1 inch, a 1 to 2. This allows us to measure in 10,000ths of an inch on diameters, thicknesses of parts that may be critical depending upon their application. Micrometers made by the folks at Starrett, Mitutoyo, or Brown & Sharp would be my recommendation to put in your toolbox. Having a good depth mic again is important if we're cutting a lot of slots, boring a lot of holes, and we need an accurate depth. A depth mic is far more precise than our dial calipers. Again, it's not a very expensive tool. It's one that's well worth adding to your list of inspection materials. While we're in the micrometer departments, let's take a look at a specialty micrometer. If we're doing a lot of boring work and we need to check wall thickness, a thickness or neck thickness or tubing micrometer is the obvious choice. We've got a football shaped spindle here that our anvil comes in contact with, allows us to measure very thin sections or cross sections of tubing, slots, material thickness, etc. Again, this has got a 1/10 indicator on it. It's got a very convenient soft stop ratchet system that we can get very precise measurements in the 10,000ths of an inch classification. If you're doing a lot of hole boring, they make an inside caliper, which is really a neat little tool. It's not real precise, but again, if we're holding hole diameters to 1,000ths or 2, this product will work just fine. We simply compress the legs, insert them into a desired hole, and allow them to spring out. If you're doing very precise work in hole diameters, having a good set of telescoping gauge or ball mics is something that's going to be very critical to you. Keep in mind that a V-block can serve as an excellent inspection tool. We can simply clamp a part that we need to measure or inspect in the V-block, clamp it down to the mill bed, hold it in the vise, and again take some very careful measurements either with our dial calipers or our micrometer depending upon our application, and again, the preciseness of the finished part. Remember, when we're using a micrometer and we're measuring in 10,000ths of an inch, it's necessary that we use our soft stop ratchet system located on the end of the mic. 2 or 3 clicks, you can hear those audible clicks, and this allows us a very precise reading from the micrometer. If we're doing a lot of inspection work in flat stock or round parts that we need to have a uniform thickness with, another handy inspection tool, if you're doing a lot of parts and need to check them accurately and quickly, is a little surface stand fitted with a dial indicator. This particular dial indicator is made by the folks at Mitutoyo. It measures in 0.5 increments. So we would simply set our standard with a quality part, a finished part, a master part, whatever the case may be, zero our indicator, grab a handful of parts that we've just machined, run them across, and very rapidly we can check to 0.5 increments as to how precise the manufacturing process is that we're engaged in. It's got a real neat veneer adjustment, so we can preload and make any necessary adjustments simply by clamping and using the veneer dial to fine-tune our indicator. If you need to check concentricity, here's a simple gauge that we build in the shop that you can do as well. We've got a dial indicator mounted on an adjustable slide, moves back and forth relative to our base plate. We've got some ground contact points that again are indexable for different lengths of parts that we may want to check. We've got a dowel pin pressed in the back. We can simply install a part for inspection, adjust our dial indicator to the desired part that we want to check concentricity with our index finger roll the cartridge case, and we can see we've got about 1/1000th variation on the dial there as we rotate the case. So this is a good example of a tool that you can build. You don't necessarily have to buy all of your inspection equipment. Again, with a little bit of creativity and ingenuity on your part, you're more than capable of designing and building your own test fixtures to aid and assist you in the type of parts that you desire to manufacture. Let's stroll over to the surface plate, and I'll show you some tips and tricks about proper layout as well as inspection of different parts using a height gauge on the surface plate. Another handy accessory in the machine shop is a surface plate or layout table. They come in granite and steel. You can get them in a variety of sizes and different grades. We have tool room grade, inspection grade, laboratory grade. For all practical purposes, outside of satisfying one's ego, any tool room grade will work just fine for 99.99% of all of the layout and inspection work that you may encounter. If you feel that you need a laboratory grade, keep in mind, in order to take advantage of the laboratory grade's flatness and uniformity, you're going to need to keep that surface plate in a controlled environment, free from dust and at a temperature of around 68 to 72 degrees. All right, enough said on that. Let's move on to the usefulness of the surface plate. We can have a height gauge. Again, a nice accessory. The height gauge allows us to perform some very complicated layout projects fast and efficient. If we've got some blocks that we need to lay out, as in this one that we've die-cummed as an example, we want to lay a hole pattern out, we'll simply adjust our scribe to a specific height, hold our block on, just drag the contact point across it, and scribe the reference lines that we need to drill holes, mill slots. Whatever the case may be, if we wanted to drill tap holes, cut slots along those reference lines, it's a very fast and efficient tool. Also, if we want to check the height of something and use it as a go, no-go gauge, we simply adjust our height gauge and contact to our specified tolerance. It's a little bit tight there. and it simply becomes a go, no-go gauge at this point. It's got a vernier scale reading on the side. We talked about that earlier. It's got a nice magnifying lens, which is a handy feature, allowing you to very precisely locate and read the exact amount of thousandths that we are scribing or gauging off of. Let's take a look at a sine bar. We've talked a lot about angles, how to set them up. We haven't really gone over the sine bar. This is an example of a sine bar. Keep in mind that all sine bars are based on a 5-inch measurement from the contact points. And simply by looking up our trigonomic factors in the logarithm sections, we will determine the amount of shim or riser block that we need to put underneath the sine bar in order to give us a specific angle. Remember, all of your trig functions are located in your machinery's handbook. Again, it's an excellent reference source for setting angles based on trig factors. A neat accessory when working with a sine bar is to use an adjustable parallel. Simply set our adjustment to whatever height designated by our reference source, insert it underneath the sine bar, and now we've established the correct angle. Lock our adjustable parallel in place. We're ready to set parts on that location, machine whatever angles we need to based on our sine bar calculations. You can also use the sine bar as an inspection tool. If we had a specific angle that we were machining on a part, we needed to reference that. We simply dial our sine bar into place. We can use a height gauge. We can also use an angle block to check those dimensions as well. If we sight down something, if we look closely now at that parallel surface, okay, we can see just how precise of an angle we actually cut. The eye itself can usually see 1 to 2 thousandths without a problem in terms of light or angle when we have something against it as a backer. Anytime we have a straight edge, we can also use a straight edge in terms of checking something. The machinist square that we showed you earlier, again, is an excellent reference on the layout table for checking perpendicularity of parts. Keep in mind the surface table is extremely flat, so it becomes a workbench itself. We want to take good care of our surface plate. We don't put any harsh solvents on it. We don't scratch or scribe on the plate itself. Coating it with a little bit of WD-40 or spray oil, keeping it clean and slick, is a nice advantage. Also keep in mind when looking at something, as we hold it up to the eye and look, if we have light as a backdrop, that allows us to check the flatness of a part as well. A long straight edge is pretty handy as well, and again, the surface plate being flat and true also becomes a straight edge. These things, again, with a little ingenuity, allow us to check parts and pieces. A 1, 2, 3 block, we use those in the mill as a parallel. They also are a useful accessory on the layout table in conjunction with our machinist square. We can set a part in place, locate it with the square, check it for flatness and perpendicularity, all at the same time, any position that we want. Another useful tool is our contact points. Remember, we talked about taking an in-mill stub, sending it off to the grind shop, and having them grind a sharp 60-degree point on it. When we've done layout work, as in our layout block, this would simply go in the mill. We would simply mount our sharpened point in a drill chuck, come over to our scribe line, locate it, and we're ready to drill if it's a non-critical part. So if we're doing fast work, that's a good tip to keep in the back of your mind. Next, we've got radius gauges. Remember, we machined some specific radiuses on our test block. If we were to check those, or if we were in doubt as to the type of radius that we were dealing with, we have a complete set of radius gauges at our disposal. Okay, let's take a few minutes and go over how to properly use the radius gauge. Little corner that you see is for checking an exterior radius. This is for checking an interior radius. Let's say we've taken a ball end mill and we've machined a groove or a slot in something and it needs a specified radius. Again, for checking an exterior radius, Simply set that over the part. Let's take a look at our block now and check some of the radiuses, and you can see the radius gauge in application. Okay, we can see the radius we've cut is quite a bit smaller than what we have in this specific gauge. Now we'll use a 13/16 gauge. Just a little bit tight. We can see the light underneath it, so it's a very precise way of measuring a radius, or using as an example to call out a radius on a part that we may have designed and we want to send out for additional machining. We can also use the end of the gauge again as an exterior radius, rotating it over the part. Obviously, if we were to put our 1/4" radius gauge, we would match our radius perfectly. Remember, we machined these surfaces with a 1/4" rounding end mill. All right, that pretty well covers the use of the layout table, some different types of inspection tools. Keep in mind the level of inspection that you need to obtain for the parts that you are machining. Dial indicators, test equipment is very expensive depending upon the application. Try and use the existing tools that you have available. Our dial calipers, a good layout table, a height gauge, a micrometer, radius gauges, an angle block, our sign bar, are all tools that we can use very effectively in establishing the quality control on the parts that we're manufacturing. Now let's use our inspection methods and knowledge to check our block that we machined. Your block should look something like this. All of the surfaces should be smooth and shiny, like a mirror. We could signal the cavalry from across the canyon. Let's start with our large flat and deal with the thickness of the part. That thickness should be exactly 1 inch, 200 thousandths, plus or minus a thou. Let's check the width of the part now using the dial calipers. The width of the part should be 2 inches, 625 thousandths, plus or minus a thousandths. Let's now move to the length of the part. That should be 3 inches, 900 thousandths, again, plus or minus a thousandths. The hole that we bored in the top of our part, its diameter should be 1 inch and 50 thousandths, plus or minus 2. The depth of the hole, and we're going to use our dial caliper, and then we'll switch over to a depth mic, which is a much more precise method of the hole. With the dial caliper we get 695 thousandths. Now let's check it with a depth mic and see if they concur. Anytime that we use a depth mic, it's really important that we place our fingers along the frame, holding it firm against the base from which we are measuring. Then use our soft stop click adjustment in order to get an accurate, repeatable dimension. Our dimension is 693 thousandths on the depth mic. So you can see the dial caliper, if used correctly, is going to get you pretty close. Again, we would select the proper tool depending upon the accuracy of the inspection. Now let's rotate the block up and take a look at the slot that we machined. There's a couple of important dimensions there. Let's use our depth mic and establish the depth of our slot. That should be 500 thousandths. Remember, we made 2 passes with the mill cutter, 250 thousandths at a time. We've got a depth of 503 thousandths. Go over to the other end and check it as well. 503 thousandths. So that tells us that we had our part held securely in the vise. We didn't have any chips or debris underneath our bar that would have affected the accuracy of the bar. Now you'll also notice that we've got a second shelf, and that shelf should be a depth of 250 thousandths. Again, using the depth mic, we'll run down and check that depth. Okay, and we've got 252 thousandths. Again, within tolerance. Now it's time to check the width of the slot. Remember, when we machined the slot, we used a smaller cutter, and we asked that you offset the cutter left and right in order to widen the slot to a dimension of a 1/2 inch. Our part measures exactly 1/2 inch. You have a tolerance there of plus or minus 2 thousandths. We'll rotate the block now and take a look at the hole pattern that we drilled in the bottom of the block. We located the center of the block, drilled a 1/2 inch hole, then we proceeded to locate and drill and ream 4 1/4 inch holes. You'll notice that you have dowel pins supplied with your block. Once we've drilled and reamed those holes and we've checked our other part and it passes inspection, insert the dowel pins in the hole. Use a ball peen hammer, set them up on a carpeted bench or a wooden block, and seat the dowel pins to the depth of your hole. We'll now measure and check for hole accuracy by measuring across the dowel pins. That dimension should be 1 inch 625 thousandths. Lengthwise on the pin should be 2 inches 900 thousandths. Rotate around to the back side, and again that dimension is 2 inches 625 thousandths. I don't want to see a variation any greater than 3 thousandths off of those dimensions. If so, a couple of things have occurred. You didn't take the backlash out of our dials when we locked the gibs in reverse direction. You drove the dowel pin in at a poor angle. Make sure that the dowel pins are driven in to the hole uniformly and squarely. We don't want them tilted or canted. Now let's rotate the block up and check the 3 holes that we drilled and tapped along the top edge. Those holes are spaced on 1 inch centers. We've centered them in the width of our block. Now, a neat little trick that you can use in the inspection room is simply use a screw, thread it into the hole, go in at least 1.5 diameters to 2 diameters of threads in order to get an accurate positioning of the screw. Then we're simply going to measure outside dimension and subtract the diameter of the screw, and this will give us our center line dimension. Keep in mind though that not all screws are exactly 1/4 inch, so you need to make a diameter check on those screws and keep that in mind when we get our overall dimension. Our screw diameters are running around 247 to 248 thousandths, and I have 1 inch 245 thousandths across the screws. So if we were to subtract 245 thousandths, that would give us the 1 inch center line that we require. Simply remove one screw into the next hole, and we're going to repeat that process. Okay, we'll grab our dial calipers and measure across the next 2 holes. And we've got a dimension of 1 inch 246 thousandths. So we've done an excellent job of establishing those holes on 1 inch center lines. Anytime that we have a bolt pattern to check, simply screwing in good screws, measuring across the outside diameters and subtracting the diameter of the part in order to establish the center line is a very easy method of locating and checking the accuracy of those holes. All right, now we want to inspect and make sure that the hole is centered in the thickness of our part. To do that, we have several options. We can set the block down in this fashion, use our depth mic over the edge, come down in contact with the screw, add 1/8 of an inch to that dimension. Okay, we've got 477 thousandths. If we add 125 thousandths to it, assuming that our screw diameter is a full 1/4 inch, that would give us a dimension of 602 thousandths. Let's go back and measure the thickness of the part. Is 1 inch 200 thousandths. Divide that by 2 is 600 thousandths. So we're within a couple of thou of having those screws centered precisely. Now our last bit of inspection is involving our center hole. How do we find out if that's precisely located? If it's a 1/2 inch hole that we've drilled, we could take a 1/2 inch dowel pin, insert it through the hole. We could use our height gauge to come in and reference off of that, indexing the part around and checking that dimension, or we can simply set it on our layout table using our dial calipers, measure from one end of the block to the other side of the block, index our block, and repeat that in 4 dimensions. Okay, and that will tell us if we have centered the hole properly. Keep in mind, anytime that we're drilling a thick piece of material, and by thick I mean 1 inch of thickness or greater, the drill is going to have a tendency to walk. Okay, so we want to keep that in mind in our tolerance levels. If we're going to be working on a real critical hole through a thick part, we would simply drill it undersize, set up our boring tool, and come in and bore to size in order to true the hole, and then we could ream to a specific size from there, because that drill will have a tendency to walk through the part depending upon how much cutting fluid we're using, how sharp the drill is, how much physical exertion we're applying on the quill in order to drill through our existing part. All right, that pretty well covers the inspection of our block. I hope that yours is passed. Now let's take a few minutes and review what we've learned in this course. We've shown you the proper safety methods to use. Remember to always wear eye protection. If we're operating a machine that's loud and noisy, by all means, grab a set of earmuffs. If we're dealing with cutting fluids or in an area that is not well ventilated and we're producing a lot of toxic fumes, hook up a fan, put on a respirator. We don't want to be breathing those bad news fumes emitted from the cutting solvents that we are using. If you don't like paying the barber to clip your hair, put it up in a rubber band, a ponytail, tuck it in your shirt, or wear a hairnet. The last thing I want to see is somebody that got a haircut by having their hair sucked into a mill cutter, a drill press, or over the lathe. Keep that in mind. A lot of accidents occur every year because somebody gets their hair caught in the machine. Industrial accidents can happen easily if we're not careful and vigilant in our approach to safety. We've shown you the different types of machines as far as a vertical Bridgeport type machine, the Bridgeport itself, the aftermarket copies, what to look for in a new and a used machine. We've covered a lot of the accessories that are available, allowing you to do much more sophisticated jobs on the mill. Rotary tables, super indexers, standard spin fixtures. We've shown you the proper use of parallels, some tips and tricks to get your peanuts out of the fire, should they get there, paper shims, how to properly protect the part. We've shown you the correct use of fly cutters, standard mill cutters. We've shown you how to care and maintain those cutters for maximum life and efficiency. Never put your cutters all sandwiched together in a bag or a box, allowing them to rattle and clang around, because we're going to be dulling or chipping those cutting edges. We've gone over a lot of the aspects of multi-production parts, inspection tooling, different types of tooling that we can manufacture to allow the facility of those parts to go smoothly in a production run. Keep in mind, the imagination is a very, very important factor in becoming a good machinist. Just because somebody says it can't be done, don't take it for granted. Sit down, analyze, assess the situation, how we can hold the part, and what sequence of operations is required in order to machine that specific part. We want to always have a handle or a gripping surface on the part. Obviously, we wouldn't drill and install our 4 dowel pins and then try and machine the slot or drill and tap the holes in the other side. These dowel pins would become our Pandora's box, if you will, in trying to accurately locate and reference off of our block. Anytime that we machine a radius or a decorative cut around the part, make sure that all 4 edges match uniformly. Take pride in our work. The finished product that we turn out is a representation of ourselves. If it's sloppy, slipshod, and does not meet tolerance, we're not going to have a happy customer, and we're going to end up getting a job at the local 7-Eleven rather than operating a profitable machine shop. Well, that pretty well covers it. It's been a real pleasure working with you, and I'll look forward to seeing you in the machine shop. All right, we're ready to move to our next phase, and that is cutting slots, T-slots, and dovetails. You'll often be asked to perform these tasks in a machine shop. There's some simple tips and tricks that I'll share with you. Our first slot is going to be with a 1/2-inch cutter, 3 flute, high-speed steel, and a bar of 7075 T6 aluminum. For those of you that were pretty good at math, simply calculate the RPM speed in your head, and let's get started. Remember to choke our cutter up close. Turn on our machine. We're going to cut a slot that is a 1/2 inch deep. So we're simply going to come in contact with the workpiece by slowly raising the table until our cutter just contacts. Okay, at that point we're going to re-zero the knee, loosen the lock ring, turn our dial. We're going to take 100 thousandths at a pass. Well, let's be a big shot. Let's go 200 thousandths. Lock our y-axis down. We want a nice straight slot. We made it through to the other side. Now let's take an additional 200 thousandths. So our slot depth now is 400. Okay, now let's sneak up on our final depth. Take about 90 thousandths. Again in a roughing cut. Now if we wanted to be really precise, we would turn off the machine, take our depth mic or some sort of measuring instrument and measure the exact depth of that slot. For all practical purposes, we're going to assume that it's 490 thousandths. We're going to go ahead and take the last 10 thousandths as a finished pass. We're going to slow the feed rate down a little bit. Now, since we started pushing the cutter really fast through there, we've got kind of a ragged edge on the sides of our slot. So we can go in and clean those up, and we're going to offset the mill cutter relative to the slot 2 to 3 thousandths on each side. Adjust your cutter 3 thousandths to one side. We're going to do these in a climb cut. Okay, go over the other side. Now we've cleaned our slots up. If we're going to be machining a slot that has to be precise in width and depth, let's say we want to machine a slot that's exactly a 1/2 inch wide by a 1/2 inch deep, we couldn't do it with a 1/2 inch cutter. We'd want to use a 3/8 cutter or a 1/2 inch cutter that has been resharpened smaller than a 1/2 inch to, let's say, 480, 475, and then offset on either side, keeping the slot centered now in the piece of material in order to get the correct width as well as depth of that given slot. Now let's move on to cutting a T-slot. We'll show you a T-slot cutter. This is a Woodruff cutter, and this is what we would cut a T-slot with. If we were making a special piece of tooling, we need to keep our slot width larger than what the shank of the cutter is, depending upon the depth that we are machining. This measurement is 310 thousandths, so anything over 5/16 will allow this to track through the slot as we cut. Now let's take a look at an exact part that this type of cutter will produce. Okay, this is the type of operation that we would cut. This T-slot cutter is just going to come in and reproduce that part. We can have a locking gib in there, a washer or spacer bar that will pull something up tight against this surface. Alright, so we'll need to cut our slot initially, and we're going to cut that to a depth of 400 thousandths using a 3/8 end mill. Okay, bring our cutter in contact with the workpiece. Okay, lock our table down. Let's take 200 thousandths in a pass. And another 200 thousandths for a total depth of 400 thousandths. We'll clean up the sides of the slot. And index over 10 thousandths on each side. Okay, now take our mill back to center. We're now ready to install our Woodruff cutter. Now, due to its larger diameter, the number of teeth and the type of teeth that it has, we're going to have to turn that Woodruff cutter a lot slower than we would the ordinary end mill. I'm going to slow that down to about 660 RPM. Make sure and use plenty of fluid. Okay, now we're going to bring the cutter in close to the work, and we want to start that T-slot right at the base of our slot. So two ways that we can do it. We can simply clear the chips out of the slot, bring the cutter in, line up a tooth and a flute inside the slot, bring the quill down until we have contact, lock the quill down, or we can start at the top like we did with our cutter initially, contact the top, raise the knee 400 thousandths. Whatever works for you will work for me. Both methods are acceptable. All right, now watch slowly as we enter the cutter into the workpiece. Make sure and use lots of fluid. Voila, you've cut your first T-slot. Pretty simple, yet a very vital thing to know when we're building a piece of tooling. We may even want to manufacture a little mill bed, and we're going to need some T-slots in it to clamp a part down, or a tooling fixture, and we'll also build some companion T-nuts to go in those slots in order to hold a fixture or a part down. Okay, so that's how we produce a T-slot. Let's go to the next type of slot, or what can be referred to as a slot of a different shape called a dovetail. We have a special dovetail cutter. Now keep in mind, when we prepare a dovetail, again, we need to have clearance here at the top of the shank in order for the dovetail to pass through the material. So we can take our dial calipers, measure that, or if we're trying to duplicate a dovetail that's, say, a little bit wider, we'd simply cut a wider slot as our sample or as the print requires. Now, look at how many flutes that we have on the dovetail cutter, very similar to the Woodruff cutter. So again, we're going to be turning this at a slower RPM than what we would if we were using a standard end mill. All right, so let's make our slot for the dovetail and get started. Make sure and choke your cutters up. We don't want a lot of exposed cutter hanging down below the collet. We want to have rigid work setups, and we want to have rigid cutter setups. Okay, we'll bring our tool down in contact. We're going to cut another 3/8 slot. Better speed up the RPM on that, hadn't we? Left it in the Woodruff cutting mode. There, that sounds a little better. All right, let's cut this slot 250 thousandths deep, and let's take it all in one pass. Install our dovetail cutter. Kick our speed down. Okay, and again, the same rule applies as with the Woodruff cutter. We can come in and make contact on the top of the part, dial down 250 thousandths, or we can just take a tooth, line it up with the slot, contact our work, back the cutter out, turn it on. We're now ready to go. Again, a lot of lubricant on that cutter. Listen to the cutter as it enters the material. Okay, you can see we've got 3 different types of slots now. Standard conventional slot using a standard end mill, a T-slot using a standard end mill and a Woodruff cutter, and a dovetail slot. If you're working in the gun trade, you'll be asked to cut a lot of dovetails to push in front sights. If you're working on a gib, this is the type of style you can use. Cut a dovetail in order to be able to adjust something for tension. Now, if we simply want to widen the dovetail, we just index the cutter left or right. I prefer to climb cut and just take a few thousandths at a pass so we have a beautiful finish on the inside of our dovetail. You can file a little bit on the edge of the dovetail so we create a starting point if we have a filler block or another piece of material that we're trying to mate. Dovetails come in all shapes and sizes. You've got 45 degree, 60 degree, 82 degree dovetails, so be specific when you call out for a part that has a dovetail in the machining process. Now, let's go over and we will do a stepped slot using a smaller cutter and show you how to expand that cutter for a wider width slot. Okay, bring our cutter in contact with the work. We'll cut a depth of 400 thousandths. Raise the slot up 200. Okay, let's take 400 thousandths all in one pass, see how the cutter responds. Okay, no problem. Outside of a cloud of billowing secondhand smoke, we achieved that cut in one pass. Now, let's go ahead and lower the mill bed 200 thousandths. And off of that same setting, we've now got a 3/8 slot. We're going to want to make it a 1/2 inch wide at the top. So a half minus 3/8 is 1/8, or 62.5 thousandths per side. So you're simply going to lock down your gibs, take the backlash out of our dial by turning it in the direction that we want, adjust our lock ring and adjust our bezel to read at 0, and we're going to index over 62.5 thousandths. 10, 20, 30, 40, 50, 62.5 thousandths. Lock the bed down. Okay. Keep the bed locked. Take the backlash out going the other direction. Set it at 0. 62.5 plus 62.5 is 1/8. So I simply go the other direction, 125 thousandths. We're now going to cut the other edge of that slot. All right, there we have it. Very, very easy to do. We've made a larger slot with a smaller cutter. We've made the two kind of an inverted U there for any width that we want. So we've got 4 different types of slots, and let's review them from the beginning. We've got just a standard slot done with a 1/2 inch mill cutter. We have the T slot, which is very popular in the use of tooling. We've got a dovetail, and then we've got another standard slot that we've just opened up at the top to accept another part. Very simple and easy to do. Remember, we want to have the appropriate cutting speeds. We want to take careful measurements for the width and depth of the slot. If we are calling for a specific width of a slot, we have to use a cutter that is smaller than the desired width of the slot, so we can come and clean up the sides once we've bulked out the material. Remember, when we're cutting a dovetail, it's always advisable to remove a bulk of the material by slotting the top of the dovetail first, and then come in with your dovetail cutter and bring it to size. All right, that pretty well concludes slots, T-slots, and dovetails. Let's move forward. All right, it's time for another tech tip. We've tried to emphasize throughout the course that it's imperative that you keep your vice jaws clean, free of chips and debris that may damage the part or affect its accuracy during the machining process. Another tip is taking a piece of 3x5 card or a piece of notebook paper, inserting it between the vice jaw and our workpiece. Okay, make sure that we're pushing down as we gently close the vise and tap it in place. Now, from time to time, we're going to get that piece of paper impregnated with chips. Simply pitch it in the garbage can, snip another one out with a pair of scissors, keep those papers clean, and you'll go a long ways towards protecting the surface finish of your part. Now, our next operation is machining a slot through the top of the block for a depth of a 1/2 inch, and then we're going to widen the top of the slot using a smaller diameter cutter, getting used to offsetting a cutter to a specific dimension. So the tools you're going to need for this operation, again the edge finder and a 3/8 end mill. We're going to go ahead and take advantage of that servo power feed on this operation since we're removing a lot of material. We want as smooth and uniform a cut in the bottom of the channel as we can. All right, make sure that the back of our part is free from any chips. And go ahead and turn the machine on, bring our edge finder down. Come in contact with the workpiece. 0 our digital. Now come over to the center of our part. Okay, we want to machine our slot depth initially to 500 thousandths. We're going to take it in 2 passes. We're going to come in contact with our work with the cutter, zero out the knee, fire up that servo power feed. All right, bring our cutter over the top of the workpiece and we're going to spot on it. There we go. Back it away. Zero the knee. $250 thousandths at a pass. Okay, before we start the servo feed up, how many of you remember to change speeds on the motor? We're turning now at approximately 1115 RPM from the last milling operation. We need to speed that 3/8 cutter up a little bit, so let's turn the machine off, switch gears now, and let's crank it up around 1750 or a little faster depending upon your particular mill. Make sure and have everything locked down. Nice, smooth, uniform cut. Make sure you apply plenty of fluid to it. We're removing a lot of material now. Anytime that we're taking a real heavy cut, it's also not a bad idea to use a manual feed. We can feel a little bit better. With the power feed on, it's real hard to tell what's going on. That cutter is simply burying its way through the chips. We've got to keep a lot of cutting fluid on it as we go. Okay, shut our servo down. Take our little acid brush and clear all the chips out. We've got a pretty nice looking channel. Okay, going to increase our depth another 250 thousandths for our final pass. All right, change our feed selector on the servo and we're off and running. If you're going to be machining a lot of aluminum and you don't want to spend big bucks for exotic types of cutting fluids, I suggest you get a little stock going in the WD-40 company. It's a very effective machining lubricant, works really well on aluminum, and also it's very cost effective, comes in its own easy applicator can. Okay, we're going to clear all the chips out, shut our servo down. Now we're going to lower the bed 250 thousandths. We're going to make the top of the slot a 1/2 inch. 375 minus a 1/2 inch is 125 thousandths, so we're going to want to cut 62.5 thousandths on either side of that slot. We're going to want to climb cut in each direction, so make sure that you have your cutter on the right side of the part. Reverse directions, offset in the opposite direction now. Okay, let's shut our machine down, and with our dial calipers, take a measurement of that slot. We should be right around 500 thousandths of an inch. Okay, we're on the money. All right, we've successfully completed cutting our slot. We cut it to a depth of a ½ inch. We lowered the bed 250 thousandths and then proceeded to widen the slot to a dimension of 0.500. We're going to allow you a thou or two on that. We want you to get used to being able to offset the cutter left and right on the y-axis to machine something to a specific dimension. Another neat tip, if you'll run your finger very gently along the top edge here, you're going to feel a very razor-sharp burr. It's kind of a pain in the tail in order to get that off, but here's another little trick. Simply take an old paint scraper type razor blade. We're going to bring the part in next to our chest, hold it against our stomach, take the edge of the razor blade, and just in a nice stroking fashion along this line, very efficiently cut the burr off of that part. Does a marvelous job of burring those internal slots. We turn it over, stroke it along just like the old knife sharpener guy at the fair does for you. All right, that pretty well concludes the steps on manufacturing our block. For those of you that live in a high-rise on Wall Street or work down at the bank, wouldn't this make a marvelous paperweight? Quite a conversation piece for the individual coming and asking for a loan. An integral part of any machine shop is its ability to design and build tools and fixtures for high production jobs. There's some very simple things that we can purchase right over the counter to very elaborate things that we can build to hold specific parts for second and third operations. So really the imagination is the limit when it comes to different holding fixtures. Let's take a look at a few simple ones and their designs and how they work for high production parts. The simplest is just a basic production stop. Little spring-loaded gizmo. We showed you this earlier and how it mounts on our machine vise. Okay, we're simply going to install it over the top of the jaw, and at this point we've established one of the simplest work-holding fixtures going. Any type of part that we do that we slide into the vise simply comes up and comes in contact as a stop, limiting fore and aft movement. We want to be sure and keep the chips out when we're using this type of a work stop. This is another fixture that we've done. Rather than put our part into an indexing head for work in the Bridgeport, we've simply taken a piece of round stock, machined 4 flats 90 degrees apart around this. This acts as a locating fixture for us. As an example, we can set it on our tooling block here. For just a reference, in this position we can come in, drill holes, mill slots, index the part 90 degrees, come in for another series of holes, index it another 90 degrees, and repeat the same operations. This, in conjunction with the work stop, is a very efficient way to produce this part. You don't have to go through a lot of elaborate tooling costs. It's just simple Yankee ingenuity, if you will, in order to perform these tasks. All right, now let's take a look at another type of fixture, something that's a little more elaborate. It's going to require the use of a couple of parallels to hold it up in the vise. And while we're on the subject of parallels, let's take a look at a unique type of parallel called an adjustable parallel. This is an adjustable parallel, and you can see that it is on a dovetailed slide. So we can either increase or decrease the height simply by sliding the two back and forth. If we have a special job that we need to mount very high in the vise, we can simply use an adjustable parallel and fine-tune the height. Parallels come in a variety of different sizes. Oftentimes, if we're dealing with a difficult part, though, we need to have something that is fully adjustable, allowing us to grip the part accurately for our next machining operation. In order to lock it in place, we simply take our screwdriver, once we've adjusted it to the proper height, and cinch these little gib screws, if you will, holding it in place. Now it's solid, just like a conventional parallel. These come in sets. They're available from all of the different tool manufacturers, so get out a copy of your MSC catalog, look under adjustable parallels, a great addition to your machine shop. All right, now let's take a look at another tooling fixture. This is a special tooling fixture that we design and manufacture for drilling holes in this little lug. You can see that we've used 3 dowel pins strategically located to align the part. We've built a little clamp that will come into place, and when the lug is held against those 3 pins, we simply tighten the clamp. It's going to set inside our vise jaws, so again, doesn't require tearing down the mill in order to get the job done. We simply clamp our fixture in the vise. We'd come in with our coax indicator, indicate the center of our bore in the lug, and then have the correct amount of offset, enabling us to drill this hole. Part after part, we simply keep the chips out of the way, align it, put our little step clamp over the top, tighten it down, center drill it with the appropriate size drill, and we're ready to go. So now you're getting an idea of just how simple some fixtures can be to hold apart. Alignment becomes critical. We need to be working off of different surfaces that we can control in the earlier machining process of the part. Try and keep in mind, anytime that we are locating something, it's got to be repeatable. If this dimension is varying, if this dimension is varying, that's going to throw a wrench in the gears as to our ability to locate that hole accurately. So it must work in conjunction with tolerance levels to be able to have consistency in our parts. If these dimensions varied considerably, but our hole was very consistent, we would use the hole then as a location. We would use something in a large pin that fit that particular hole and simply sleeve the part over the top, align it possibly with a dowel pin here or a pushing removable slide, and then we could drill and locate our hole. So be flexible as to the type and design of tooling fixture to hold a specific part. Try not to have tunnel vision in the machine shop. Another unique fixture is one that we build allowing us to flute bolts for the Remington 700 series of rifles. I'll show you an example of a fluted bolt. You can see the different flutes in the bolt body. Adds a little bit of gingerbread to the rifle, reduces the weight. Very simple and easy to do. A lot of people would try and support this bolt between centers. The problem with that is that the firing pin hole and the driving hole in the back for the cocking piece and bolt shroud is not always concentric. So as we rotate this part, we get an oscillating effect of the bolt body, and our flutes do not come out parallel. So I designed a very ingenious part that allows us to lie the bolt body, which we know is cylindrical and true, into a miniature V-block. We showed you how to mill a little V-block earlier, and then simply have 2 overarm clamps to hold it in place. And again, it can come in to our vise. We always try and use the simplest hold down methods possible for time and efficiency, and we would simply rotate the bolt. We've got a removable pin in the front which acts as our work stop. We push the bolt up to that position, locating the fore and aft movement. Also controls the length and consistency of our flutes. Now for the back, in order to time it, we've machined up these little slugs that screw into the back. So once we've established the location of our flute, we simply screw this into the back of the bolt, tighten it down, and use it as a reference indicator for indexing the bolt depending upon the number of flutes that we decide to machine. We also have a larger version that you can see with all of the different facets on it, indicating a much finer flute spacing around the circumference of the bolt. And again, this would simply screw into the back of the bolt. Once we've established the location of our flute, we would simply align this and continue to rotate and reference off of the flats that have been machined on our flange. Okay, so again, very simple. Tooling does not have to be complex. The Russians had a pretty decent idea during World War II in the design and construction of a lot of their tools and armaments. The designers were given the types of tools that their product must be produced on, a welder, a riveter, a saw, whatever. Those were the limitations, and they had to try and design specific parts and pieces around those toolings. They didn't have the luxury that we did in America at that time with a vast manufacturing facilities with all of the latest design techniques, developments, tools, machines, etc. They were very limited, yet they managed to produce a considerable amount of production with those limitations. All right, another fixture that is relatively inexpensive, comes in awfully handy, is the very simple spin fixture. Very simple and easy to do. It works off of a 5C collet. It's divided into degrees, and we can simply rotate this around for drilling hole patterns, machining flats, facets, whatever we need to do. Let's take a look at the back and how it operates. You can see we've got a degree wheel on the back. We could clamp this in our vise or simply bolt it to the table. It is graduated in 5-degree increments for a total of 360 degrees. We can look, and very similar to the veneer that we looked at earlier, we have a hole spacing across the bottom and an index pin. The index pin, when it is left on 0, okay, that indexes in 10-degree increments. If we want to break it down even finer, we have holes marked 1, 2, 3, 4, 5, all the way to 9, varying those amount of degrees on the index spacing. It's not extremely accurate. It's not like having a rotary table or a manual indexing head, but it's good enough for the majority of simple indexing practices that you may encounter in the shop. Simply start at 0 with your index, pin in the 0 hole. If we want to drill something in 30-degree increments, simply turn it, locate our pin, make our machining operation, remove the pin, index, so on and so forth, all the way around the circumference of our part. A worthwhile addition to the machine shop for simple indexing. Okay? If you're going to get into complex indexing, by all means, you're going to need a rotary table or an indexing head that divides the circle up into degrees, minutes, and seconds, depending upon how accurate your application is. All right, that pretty well covers a lot of the simple fixtures. Now let's take a look at some more complicated, more expensive fixtures for the mill. Our next tool for review is the rotary table. This is a horizontal vertical rotary table, a very precise instrument. We showed you the spin index fixture earlier, and it'll get you by for most machine shop applications, again, depending upon the accuracy. But when we need extreme accuracy, the rotary table comes into play. In order to set your rotary table up, first we need to clean our bed off, make sure that the bottom of the rotary table is free of chips and burrs, and then we're going to mount that directly to the table. We are going to dial indicate the spindle over the spindle hole in the rotary table, and we can use our coax indicator to achieve that in just a few seconds. The rotary table is ideal for doing hole patterns, milling circles, cams, ovals, things of this nature where complex milling operations come into play. Once we've dial indicated the spindle directly over the spindle of the rotary table, then we simply offset in the X or Y axis for a specific diameter hole pattern and begin to advance the hand wheel, breaking up that hole pattern in a number of degrees depending upon the number of holes in a 360-degree circle. This particular rotary table is set up in minutes and degrees. We have 360 degrees in a circle. We have 60 minutes in a degree and 60 seconds in a minute. So you can see with a precision rotary table just how fine we're breaking that circle up in terms of its rotational degree arcs. If we look closely now at the dial and we were ready to start a hole pattern, we have 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, 60 minutes, and 1 degree in the rotation of our hand wheel. We've got some little lock breaks on the sides of the rotary table. So let's say that we were doing a 10-hole pattern and we needed to index those holes every 36 degrees. We would simply advance the hand wheel the appropriate number of revolutions in order to go 36 degrees. We're going to put our little brakes, if you will, on. These are locking gibs on the rotary table. Drill, countersink, tap our hole, loosen them up, continue to index around to our next 36-degree hole spacing, repeat the process for a total of 10 holes or 360 degrees. The repeatability and the accuracy of a rotary table is nothing short of phenomenal. Turned in the vertical position, we can mount a chuck through the spindle hole. This particular spindle hole has a Morse taper. We'll show you as an example by inserting the Albrecht chuck in its place. Just visualize this as a lathe chuck where we can grab and hold parts in a vertical or horizontal position for machining. Now let's say that we've got a block and we need to machine a radius or a circle or do a hole pattern in it. We would simply set our block on the rotary table. Again, keep in mind we've indicated the spindle directly over the spindle hole in the rotary table. We can take our step clamps, hold our workpiece to the bed, index off the appropriate amount depending upon the diameter of the hole pattern, and then proceed to rotate and machine. Anytime that we are machining on a rotary table where we're using an end mill to cut a circle or cut a cam, our direction of rotation is such that we want the cutter to be conventional mill cutting. We don't want to be climb cutting around trying to suck that cutter or the worm feed of the rotary table into the cutter. We always rotate the table in the direction so we can use a conventional milling process. That's very, very important. That allows our rotary table to last a long time, prevents injury to the workpiece or ourselves if we happen to suck the part out or break a cutter trying to climb cut on the rotary table. All right, that pretty well covers the rotary table. I'm going to go ahead and flip it up into the vertical position so you can get a perspective again of the versatility involved in a rotary table. Remember we talked earlier about our spacers on the bottom of our mill vise. Well, the same thing has been done here on the rotary table, so we would simply invert this, line it up in the T-slot, pull it to one side where both of these rail edges align, and that's going to pretty well align it. So let's go ahead and give that a try. Keep in mind rotary tables are quite heavy, so make sure you have some eggs for breakfast or Wheaties in order to hoist that around. Okay, there we are in a vertical position. We can continue the rotation of our part. Imagine we have a drill chuck in place or a lathe chuck. We want to continue to advance those parts, drilling, tapping a hole pattern, machining a groove, a cam, whatever the case may be. So it's a very versatile application. Again, we would lock down our gibs anytime that we were to make a drilling or milling operation, holding our workpiece very rigid.
Attention, gun owners, collectors, hobby gunsmiths, FFL dealers, and professional gunsmiths. The American Gunsmithing Institute offers you comprehensive training and information through our exclusive instructional videos. AGI's complete line of how-to gunsmithing kits will give you the results you're looking for, whether you're refinishing a stock or glass bedding a rifle. Each kit comes complete with AGI-approved products and a video instruction manual featuring a master gunsmith. Whether the process is as simple as tactical spray coating or as involved as parkerizing, we guide you step by step as only AGI can, giving you the tips and techniques you need to avoid mistakes and get professional results. In the AGI Armorers series, each course covers a specific firearm. We give a brief overview of the history, demonstrate the design and function using cutaways, and guide you step by step through complete disassembly and reassembly down to the last part. We also show proper cleaning and lubrication methods, troubleshooting tips, repair techniques, and review available accessories. No other video will give you this level of instruction on one specific firearm. We offer courses on all the popular makes and models. Want to learn more about general gunsmithing techniques? In AGI's complete practical gunsmithing course, we show you how to set up your shop, and then we cover step by step the most common gunsmithing projects. In over 4 hours of exclusive video, a master gunsmith will teach you precision scope mounting, sight installation, stock repair, cold bluing, glass bedding, recoil pad installation, how to remove a dent from a shotgun barrel, and many other tricks of the trade. If you're interested in becoming a gunsmith, the American Gunsmithing Institute is internationally recognized for our professional gunsmithing course. It contains over 100 hours of detailed instruction on 56 videotapes. Instructor Robert H. Dunlap has over 30 years of professional gunsmithing experience and has taught professionally for 20 years at one of the nation's top gunsmithing schools. He will guide you step by step through the design, troubleshooting, and repair of all types of pistols, revolvers, shotguns, rifles, and .22s. Our close-up video techniques combined with Mr. Dunlap's exclusive knowledge and unique teaching methods provide you the opportunity to become an AGI-tested, certified gunsmith. Whatever your gunsmithing needs, AGI can provide you with the knowledge and materials you need to successfully customize, repair, and refinish your firearms. For a complete catalog featuring all of the AGI products, simply contact the American Gunsmithing Institute at 1325 Imola Avenue West, number 504, Napa, California 94559, or call 1-800-797-0867. Or you can browse through our color catalog with images from the actual videos at our website. Get online with the American Gunsmithing Institute at http://www.americangunsmith.com.